Hello, and welcome to Lesson 7 of this Introduction to Differential Equations with Wolfram U. Up to this point, we have discussed some of the methods to solve linear first-order differential equations, as well as separable equations, which can be nonlinear. In this lesson, we'll discuss the concept of exact equations and how we can solve these types of differential equations. Let's take a look at an overview of this lesson. When solving linear separable equations, we saw that it is best to first transform the equation into an easily integrable form. However, not all equations are separable or linear, so the methods discussed for those types of differential equations can't always be applied. But if we are able to classify the equations as exact, then the equation can be directly solved. This lesson will discuss how this is done by examining the partial derivatives of a so-called auxiliary function. This is demonstrated by the flowchart here, where the equation at the top is separated into two parts. The blue term is obtained by differentiating the equation with respect to y of x, while the red part is obtained by differentiating with respect to x. We'll see shortly how this is relevant when solving exact equations. While these lessons discuss many ways to solve first-order ODEs, it is important to remember that not all such equations have a general method for finding a solution. To introduce the concept of exact equations, begin with the general first-order differential equation given here. In this equation, both the n and the m functions are arbitrary functions of the independent variable t and the dependent variable y of t. Let's now introduce an auxiliary function phi, which satisfies the differential relations here, that the partial derivative with respect to t of the auxiliary function is equal to the m function, while the partial derivative with respect to y of t is equal to the n function. Substituting these expressions for the m and n functions into the differential equation allows us to write the equation in this form. Recall the chain rule for the total derivative from calculus. Since the left-hand side of this chain rule equation is identical to the left-hand side of the differential equation, we can conclude that the total derivative of phi with respect to t must be equal to 0. Therefore, we can use integration to calculate the auxiliary function and show that it is equal to a constant. Let's verify that the differential equation here is exact, then find its solution. The important step is to recognize the derivative terms. The partial derivative of the auxiliary function with respect to t must equal the term not involving the derivative, so it must equal the 5e to the y term. On the other hand, the partial derivative of the auxiliary function with respect to y of t must equal the coefficient in front of the derivative term, which is the 5t e to the y of t term. Therefore, the partial phi over partial t term is equal to 5 e to the y, while the partial phi over partial y term is equal to 5t e to the y. Now that we have identified the two derivative terms, we could use integration to find phi, but it is easier to use dsolve value to find phi. Since the implicit solution for the auxiliary function equals an arbitrary constant, we can combine the two arbitrary constants to write the solution as this. This equation for the auxiliary function can then be solved for y of t to find the solution to the differential equation. We now have an expression for the auxiliary function which contains the function y of t, which solves the differential equation. Let's use solve to get an explicit expression for y of t. This result can be confirmed very easily using the Wolfram language dsolve value function. The two solutions can be seen to be equivalent using the properties of log and redefining the constant term log of c1 over 5 as another arbitrary constant c2. There is a relatively quick way to recognize a differential equation as an exact equation even when the auxiliary function is not obvious. begin with the general first-order differential equation we had considered earlier on in this lesson. If there is an auxiliary function, then it will satisfy these differential relations. The differential relations say that the m function is the partial derivative of the auxiliary function with respect to t, while the n function is the partial derivative of the auxiliary function with respect to y of t. First, apply the partial derivative with respect to t to the n function. This gives us the first line in this equation. Recall the commutability of the partial derivatives, which means that we can interchange the order of the partial derivatives with respect to t and y of t. Using the commutability of the partial derivatives gives us the second line in this equation. Noting that the partial derivative of the auxiliary function with respect to t is equal to the m function, we can arrive at the last line in this equation. Therefore, the n and the m functions are related by this differential relation. By knowing this differential relation and being able to identify the m and n functions in the differential equation, we can check if the functions satisfy this differential relation. If they do satisfy the differential relation, then we can conclude that the differential equation can be classified as exact. Let's determine if this differential equation is exact. To determine if a differential equation is exact, the differential relation we derived earlier between n and m must be satisfied. To check if this relation is satisfied, first define the m and the n functions. The n function is the term that multiplies the derivative term, while the m function is the remaining terms. Now, with the m and n functions defined, use the Wolfram language d function to calculate the derivatives. We can see that this relation is not true for all functions. Therefore, this equation is not exact. Let's now determine if the differential equation here is exact. As we saw in the previous example, we can determine if a differential equation is exact by checking if the differential relations between n and m is satisfied. First, define the terms for the m and n functions using the differential equation. With these terms defined, check the differential relation between the derivatives of the n and m functions. We can see that the relation is satisfied, so the equation is exact. Since we know now that the equation is exact, and we know how the m and the n functions relate to derivatives of the auxiliary function phi, we can find an expression for phi through integration, and thus get an implicit solution for g of x, which solves the differential equation. Integrating the m function with respect to x and the n function with respect to g of x gives this result here. Therefore, the full solution is the g times natural log of x term seen in both results, plus the 3x squared term seen in the first result, and the minus 2g term seen in the second result. Notice that these extra terms, 3x squared and minus 2g, depend only on x or only on g. So one of these terms will be 0 after applying the partial derivatives from the differential relations. We now have a solution for the auxiliary function. Setting the expression for the auxiliary function equal to an arbitrary constant gives an implicit solution for the function g of x. Now we can solve for g of x to get an explicit expression for the solution to the differential equation. It can be seen that the result we just found agrees with d-solve value. Let's determine now if this differential equation is exact and find the solution if it is exact. Like in the previous examples, we can check if this equation is exact by checking the differential relation between the n and the m functions. First, define the n function as the term multiplying the derivative term, and the m function as the other terms. Then, we can check the differential relation by using the d function. As can be seen, the differential relations are satisfied, so the differential equation is exact and we can proceed with finding the solution. We know that the equation is exact, so we know that the partial derivative of the auxiliary function with respect to x equals the m function, while the partial derivative of the auxiliary function with respect to y of x equals the n function. To find the auxiliary function, integrate the m function with respect to x and the n function with respect to y of x. There is no function dependent only on y in the result from the second integral. Therefore, the auxiliary function is the sum of the e to the 3xy term common in both results, plus the x squared over 2 term from the first integral. Finally, including the arbitrary constant to write an equation involving the solution y of x. With this equation defined, solve to obtain an explicit expression for y of x. The answer can be checked using dsolve value. The form of the two solutions are slightly different, but the two are equivalent up to an arbitrary phase factor, which is taken into account by the arbitrary constant. This lesson discussed a subclass of first-order differential equations called exact equations. Such differential equations take the general form given here. A differential equation in this form is said to be exact if its terms satisfy this differential relation. If the equation is exact, an implicit form for the solution can be found in terms of an auxiliary function. An explicit form for the solution to the differential equation can then be found by solving for y of t.